Right. Afternoon, once again. Thanks for joining us as far as another session of computer architecture is concerned. As you already know, we are looking at mass storage technologies as far as today's session is concerned. Um, I think you'll discover that this obviously, again, like we mentioned in our power supply session, this would also assist invariably in completion of your assignment as far as assessments there is concerned. Because if you remember well, I think if you've had a look at the clip that discusses what's happening with that assignment, question number 3 of your assignment is the one that is a bit more involving, looks at the dismantling of the machine. And then you also need to look at just discussing several components that are relevant as far as the system unit there is concerned, as far as configurations there would typically go. So obviously you need to discuss I think it's any 5 components within the system unit. And then obviously look at what's happening in terms of configuration, common issues, common solutions, and so on. So your hard drive or mass storage technologies are typical examples of that, because obviously we're going to be discussing hard drives in general and just understanding exactly how they function, and then ultimately also looking at the whole concept of how you can successfully troubleshoot should the need be. So it's just explaining how hard drives work, looking at identification rather of mass storage interface connections, describing how to protect data with RAID, which we'll go into detail a little later on in the session, and then obviously looking at describing how to install your distinctive hard drives. So if you remember, I think in our very first session, when we were looking at what's happening as far as computing mechanisms there is concerned, I think we discussed the whole concept of the computing process. And if you remember well, we mentioned that the computing process rather incorporates input, process, and output. That's the initial computing process that was distinctively elucidated. But obviously with the advancement of techno storage as well as networks were typically incorporated there. So obviously what this typically means is that obviously any computing device or any electronic device that we choose to label as a machine should naturally be able to input, process, output, store, and eventually also connect to a distinctive network there. So this is content that you are literally familiar with. So it's important for us to probably just go back a bit and understand exactly what's happening there, and then look at what's happening with the different types of drives that are out there, and obviously how they distinctively function. So if you go back, let's see if we can share our PowerPoint slides as usual here. All right, so like I said before, basic computing or basic computer system should naturally be able to look at input, a process, output, store, and or storage, and the whole concept of connecting to a network. So naturally, if you look at what is happening as far as your storage is concerned, so storage, if you remember well, we subdivided this into primary. And we also discussed the whole concept of secondary storage. And if you remember well, we mentioned that with primary storage, typical examples of components that fall within this particular category would be RAM, for instance. Why? Because this is the essential location that is relevant in terms of storing instruction sets that need to be executed by your central processing unit. So we've mentioned before that literally when you're looking at instruction sets, it can be very simplistic and be very complicated, whichever way you look at it. There's a whole bunch of instructions that the computer executes at any given time. So the moment you switch it on, from the moment you switch it on to the moment you switch it off, you've got instructions that are running in the background, instructions that are running directly in terms of you interfacing with the machine and so on. But in order for these instructions to be executed or to be acted on, literally they have to be stored somewhere first. So this storage platform that is responsible for storing these instructions that obviously need execution or collection and execution by the central processing unit literally would be your primary storage. That's what your primary storage main responsibility is for, just to ensure that instruction sets are kept somewhere first. So that's hence the term primary or main memory. And like we said before, typical example of that primary or main memory would be RAM, your random access memory. And one of the aspects we mentioned in terms of what characteristics are associated with primary memory is volatility. All right. So remember, what did we say in terms of volatility from an electrical point of view or from an ICT point of view? This typically just means that anything that is stored on this component or within this particular component is lost the moment power is removed or switched off. So in essence, what we're saying is, if you only want to look at it from a different perspective, assuming you've installed a program, when you run that program, literally that program is loaded into your primary memory for you to function it or to work on it. But whatever you create within that program, for instance, is then stored on your secondary memory for later retrieval, or ultimately the installation of it is on your secondary storage, and then naturally when you work with that particular program or app, it's loaded into RAM. So volatility, whatever you're working on or whatever is stored there is typically lost the moment power is removed. On the other hand, when you discuss secondary storage, another term for it is mass storage. You're now looking at storing content on a more permanent basis. So you want to store a document that you've just created for retrieval 5 minutes after, or 5 weeks after, or 5 months after. It all depends in terms of what you're looking at. But it's looking at storing content on a more permanent basis. And naturally, what it now then means is that components associated with secondary storage or secondary storage at large is non-volatile. So what that then typically means is that whatever is stored there, even if you do switch off power, even if power is removed, whatever is initially stored on that component is still accessible the next time that you switch on your computer system, or you plugging in that particular component to a different machine, whatever is stored there is still accessible. So typical examples of these. So typical examples of our secondary storage would then include such components as the hard drives, which we're going to be discussing today. And these particular hard drives can either be internal or external hard drives. And then it's important to identify some of the subdivisions associated with these hard drives. So both internal or external hard drives. So obviously, if it's internal, plugged in your system unit or within your laptop, for instance, and if it's an external components, you plug in using your external ports or your input-output ports. Your USB port is there's a typical example of that. So what you need to understand now is that when you look at these hard drives, there's a subdivision. Right? What's happening with that subdivision? What's happening with that division every which way? So whether it's internal or external, these hard drives can either be what they call HDD, SSD, or HDD. Right? Typical examples of the different types of drives that you can find. And these drives, when it's HDD, that's short for hard disk drive, normally associated with magnetic hard drives, which we'll look at in a moment. And then you've got solid state drives, which is your SSDs. And then lastly, you've got hybrid hard drives, which normally combine the architectures associated with hard disk drives and the architecture associated with SSD. So normally hybrid, as the term hybrid, normally hybrid, remember anything that is hybrid is normally a combination of more than one distinctive entity or technology, whichever way you want to look at it. So your hybrid hard drives are literally just combining your hard disk drives and your SSDs into one distinctive component. And then the other types of components you can find is optical media. So remember all your DVDs, CDs, and so on that will fall within that particular category. So optical media is something that you can discuss here. Optical media, and you also even talk about flash media. So such components as your SD cards, your thumb drives, and so on would fall within this particular category. So flash media as well. All right. So these are typical examples of. Let's see if we can write this accordingly. Right. So flash media. Hopefully that's a bit more legible. Okay, so there you have it. So that's what secondary storage is all about. I think that the main concept, I think maybe let's put a different ink here. The main concept is that as far as this particular primary storage is concerned, this is volatile. So your primary storage is volatile, and obviously your secondary storage, on the other hand, just for argument's sake, that is obviously non-volatile. So again, just that just means that whatever is stored is still accessible if the power is removed. So that's the whole concept of what's happening as far as storage there in a nutshell is concerned. All right. So if you're looking at now the hard disk drives, a typical example of these particular drives. So if you look at it from a different perspective now, these hard disk drives are known literally as magnetic hard drives. All right. So magnetic hard drive. So and another term associated with this is, or with these particular components, is your traditional hard disk drives. All right. So traditional or magnetic, one and the same thing. And normally you've got magnetic platters that compose these particular components. And within these magnetic platters, or within this particular hard drive, you've got read-write actuators. So normally these read-write actuators, also known as read-write heads, rather on actuator arms, that are typically controlled when you're looking at the whole process of reading and writing. Remember, when you're reading from a drive, you're essentially accessing content from it. And then when you're writing to a drive, you're distinctively saving content on these particular drives. So literally, like I said before, normally associated with the term traditional hard disk drives, this traditional setup is associated with magnetic or rotational drives. And in some instances, you might even find certain literatures mentioning that these are platter-based hard drives. So you've got a spindle. Obviously, we're looking at things like rotational speed. I think it's important maybe to look at what these look like from so that you can visualize exactly what it is that we're talking about in terms of storage, and then understand exactly what is happening in terms of the different speeds and access as well. So I'm going to quickly see if I can share images of these so that at least you can see what it is that we are distinctively discussing. Makes it a bit more lucid. So here, all right, so if you look at what we've got on screen, that's a typical example of an enclosed hard disk drive. The one that you see on top there is the one that is enclosed, your generic hard disk drive. And then obviously what you see on the bottom is something that is opened. You obviously rarely would need to do this, or actually not recommended at all, because that would distinctively damage if you're obviously doing it within the incorrect and inappropriate environments as far as these particular components there are concerned. So if you look at the one that's on the bottom there, you've got that circular platter that is attached to your read-write heads on actuators that are responsible for obviously movement of these read-write heads. And like we mentioned before, you're literally looking at reading from a drive, accessing content, writing to it, you're storing content associated with your distinctive environments. So these hard drives come with a set spindle speed or rotational speed. So the platters that you find, they obviously rotate every time that you boot up your machine, every time that you want to access content from it, every time that you want to store content on it. These particular magnetic platters are constantly spinning. Obviously, the more the spins, the faster the access, if you want to look at it from a different point of view. And these spins are normally measured in what they call RPMs, or revolutions per minute. So naturally, the higher the revolutions, the faster the drive would be. But obviously, there's a distinctive drawback there because it's a mechanical component, rather. What it typically then means is that the more revolutions, the more heat that is generated. So ultimately, it means that the faster drives will obviously need proper cooling to avoid them and naturally overheating, because the overheating would reduce the life of that particular drive itself, and at the same time can detrimentally affect, obviously, in terms of damage associated with that distinctive component. So when you look at these particular rotations or RPMs, all the drives were running approximately 3,600 revolutions per minute. And now you find that with most of these traditional hard drives, you can get up speeds of up to 15,000 revolutions per minute in terms of access there. So some of the common speeds that you'll normally find as far as these particular drives they are concerned is your 5,400, 7,200, and 15,000. Even 10 as well can be included in that particular category as far as your specific setup is concerned. So just to reiterate again, that the faster the drive is, naturally the more heat is bound to generate. You obviously need to ensure that these particular entities are cooled appropriately to avoid them crashing, to avoid obviously a detriment there. So obviously, if you look at another image here, this is a typical example now of the read-write heads on actuator arms. And naturally, like I was saying before, the whole concept of it being mechanical, it has a distinctive effect on the actual speed of the drive and the longevity of it in terms of how long that particular drive can last you in terms of usage within distinctive environments there. So these traditional drives as well would come with different form factors. So if you go back to our, see if we can go back to our PowerPoint slides, yeah? So with the magnetic drives, so we've just mentioned the whole concept of spindle speed or rotational speed. So we can mention here, or probably even before we, no, it's fine, that still works. So spindle speed, normally measured in what they call RPMs. And like we said before, that is short for revolutions per minute. And the common speeds that you find as far as basic drives now are concerned is about 5,400, 5,400 there. You can talk about 7,200. You can also even mention 10,000. And 15,000 RPM. So these are all examples of some of the common speeds that you find associated with your spindle or rotational speed. Like I said before, obviously the higher the rotations, the faster the drive would be, but obviously the more cooling mechanisms that are applicable in that environment to avoid any distinctive discrepancies there as far as your environment is concerned. So the other thing as well that you also need to take into consideration is that these magnetic drives obviously would also come, or these are drives at large, would come with what they call form factors, right? I think we already know what the term form factor means. We've mentioned form factors when we discussed motherboards. And normally the form factors associated with your distinctive magnetic drives is either 2.5 inch or 3.5 inch. Right, and the distinctive differences between these two is that normally you find that your 3.5 inch sizes are normally associated with your desktop environments. And arguably, your desktop can typically incorporate connectivity of these drives to the actual board itself using 2.5 or 3.5, but 3.5 as a sole measurement there or form factor is only applicable to your hard disk drives. Oh, sorry, your desktop machines. But on the other hand, when you're discussing laptops now, laptops literally only used one distinctive form factor when it comes to these magnetic drives or your traditional drive, and that's a 2.5 inch. So in essence, you can mention that you're from a different point of view here. If you want to be very specific about it, what we're actually mentioning rather here is a 2.5 inch is for your laptops. And your desktop, more common for your desktop is 3.5, but at the same time, your 2.5 inch or 3.5 inch would be for your desktop machines. Okay, what's happening here? There you go. Desktops. Okay. So that's the type of setup that you've got as far as your specific environments there is concerned. So when you look at these actual form factors, maybe just to give you a clue in terms of what's happening there, again, a quick switch over. So that's what your generic form factors would look like. Obviously, the one at the bottom there is the WD or Western Digital drive there. That's your generic 3.5 inch in terms of form factors and size. And the one that you see on top there, the 860 Evo rather, Samsung, is a typical example of what a 2.5 inch would look like. So one would distinctively be associated with your laptops. And then the other one, more common in your desktops, but again, like I mentioned before, your desktop environments still provide for connectivity for both 2.5 and 3.5, 3.5 being the most common one. And then when it comes to your laptops, strictly within the 2.5 environment when it comes to these traditional drives. So obviously, when you look at the whole concept of usage of the computer system, if we're talking about spindles and we're talking about rotations, we're talking about magnetic platters, read-write heads, and actuators and so on, what it then typically means is that every time you boot your machine within the traditional hard drive environment, part of the whole boot process is looking at that particular traditional hard drive needing to spin up before your read-write heads can actually retrieve data off that particular drive and then naturally load it into RAM. So that's a typical example of what would literally need to happen when you're booting a machine using your traditional hard drive environments there. So obviously the whole concept of all these moving metal parts within the platter-based drive itself would obviously use a lot of power. Remember yesterday when we were discussing the whole concept of your power supply environments, we mentioned three distinctive type of voltages. We looked at 3.5, 5, and then 12 volts. And we mentioned that the 12 volts are normally associated with the optical drives and your mechanical or traditional hard drives, because obviously they need more power in terms of usage. Obviously, the whole concept of these mechanical moving parts would need more power as far as your specific environment there is concerned. So again, a lot of heat. And as time goes on, that particular drive tends to wear off. So the issues that you'd normally find associated with magnetic drives is the whole concept of the heat that's normally generated, and also looking at the taking up of space, the wear and tear down the line, and obviously the amount of time it literally takes up to boot, and obviously the power associated with these particular drives. So to alleviate these issues or to address these issues, solid state drives were then created. And these particular solid state drives or SSDs do not have mechanical parts at all. It's all flash technology that is used within that environment, so integrated circuits that are responsible for storing or housing data within your environment. So it's the same technology that you'll find within your memory cards, your thumb drives, typical examples there as far as your setup is concerned. And normally the form factors that you'd find associated with SSD. So a typical example of what an SSD would look like is something that you've got on screen currently. So that's a 2.5-inch SSD. So the form factor would typically be one and the same. But obviously the architecture behind or within it, if you want to look at it from a different point of view, is distinctively different there. So you also have other form factors that are associated with your SSDs or your solid state drives, which are known as M.2 SSD. So this is more or less something that would probably just mimic a RAM module that you then plug in on the relevant slot as far as your specific motherboards they are concerned. So a typical example now of what an M.2, so this is a typical example of a 2.5-inch SSD that you can either plug into within your laptops or desktop environments. And then if you're looking at the M.2 now, this is what you've got on screen. So this is the same concept. It's literally still an SSD. The only difference now is the actual form factor and the connection or where it typically then plugs in as far as your specific environments is concerned. So this plugs in again within your laptop environments, but you also might find some desktop boards that would typically enable you to plug it into the desktop as far as your specific setups there is concerned. So SSD is a lot faster as compared to your traditional hard drives, like we said before, because there are no mechanical parts. Literally, we don't have to spend time having to have the actual drive itself kind of wake up, having the read-write heads start working, having the platters start spinning, and then literally accessing content using those read-write heads on the actuators we were talking about earlier on. So it becomes a lot faster from a distinctive point of view. And obviously, when this particular technology was initially introduced, it was rather expensive. I mean, obviously, comparing with your traditional hard drive, it's still within the same category now, but the prices have literally gone down because most of the machines, both desktop and otherwise, that you'd find, and obviously with the inclusive of the laptops that we were just mentioning earlier on, now come with your SSDs as basic storage devices. So there was a time a couple of years back where SSDs were ridiculously expensive, both internal and external environments. But now, because of them becoming more common, literally the prices are not as bad as they were when they were initially introduced, which normally happens with all types of techno, really. So now you still find that, yes, if you were to compare a laptop that you'd go into a shop and buy that has an SSD versus one that has a traditional drive, naturally the one that has an SSD is slightly more expensive, but that jump in terms of pricing is not as bad as it was before. And again, like we've mentioned before, you're literally paying for something that you see direct advantages of. Because as far as boot times are concerned, as far as accessing content, storing of content, and so on, your SSDs are a lot faster as compared to your traditional drive. So at least you know for a fact that you're good to go within those environments. I think it's important to realize that we might have mentioned this before in our previous sessions, that there's always that a misconception in certain instances that, okay, look, just plugging in more RAM as far as my machine is concerned, I should be good to go in terms of it being fast. But it doesn't work as a lone entity. So you can plug in as much RAM as you want. If you're still running a traditional drive, your machine is still slow in that respect, right? And we obviously have also mentioned the fact that you need to have a concurrent CPU that functions accordingly. Obviously, that can accommodate the X amount of RAM that you've plugged in. But if you want to look at it from a holistic point of view, really, the moment you plug in an SSD into a machine, your access times, your boot times, your usage of it generally becomes a lot faster, regardless of the actual processor that you're using, and in certain instances, the amount of RAM that you've plugged in. So remember, normally we were talking about entry-level machines sitting with about 4 gigs of RAM. Now that is really not applicable in terms of usage. So you're looking at probably an 8 gig machine, even if it's running an entry-level processor. With an 8 gig machine that has got an SSD plugged in, you'll have a chunk in terms of time saved as far as access and usage there is concerned. So I think it's important to understand, without obviously sounding like a broken record, that your SSDs are hugely faster than your traditional drives in that respect, because obviously this one does not have any mechanical parts as compared to your traditional drive, as far as your setup there is concerned. So SSDs, like I said, more costly, but literally you can look at it from a relative point of view in terms of the actual technology that is used within your specific environment there. So normally you find that certain SSDs would use what they call MLC, or multi-level cell memory technology, in place of a more efficient single-level cell technology that obviously looks at cutting costs in that environment there. So how these particular drives would operate internally is by writing data rather in scattershot fashion, obviously using high-speed flash memory cells, obviously in accordance to the rules contained in internal SSD controller environments there. So obviously you could argue that there's a relationship now that happens between the actual operating system and your SSD for a faster access, because what you're literally looking at in this particular environment, the OS literally makes the SSD appear as a traditional drive because of the actual architecture that was used before, as far as these particular drives they are concerned. So a typical example of what an M2 would look like when it's plugged into the board is something that you find there on screen. You obviously have to have a dedicated port that allows you to plug in this particular M2 as far as your specific environments there are concerned. All right. So I think that does that in that specific setup as far as your particular drives there would go. And like I said before, hybrid hard disk drives or hybrid drives literally combine the technology that you find within SSDs and your traditional drives. So normally you might find, because remember, traditional drives are a lot cheaper, right? So when you look at mass storage in a hybrid drive, normally that's the part that is associated with your traditional drive. And then for the boot process, because you want your machine to boot in a fast fashion, naturally, your SSD now is the one that is responsible for that. So when you look at hybrid drives, normally the traditional part is the one that is used for mass storage because it's a lot cheaper. And then the SSD part is used for booting up the machine, running operations or running apps, running the operating system, for instance, just to make your machine obviously literally a lot faster, right? So that's the whole concept there associated with your distinctive environments as far as your drive configurations there would go. All right, so here, I think if you go back, let's see if we can quickly go back again to our notes here. Give me 2 seconds. So going back here. All right, so as I was mentioning earlier on, if you're looking at the whole concept of what's happening as far as your SSDs, so that's the second type of drive. So SSD, which is your solid state drives. And like we mentioned before, as far as this particular drive there is concerned, it uses flash technology as far as so this would uses flash technology as far as basic storage is concerned. And like we said before, it does not have any mechanical parts. That's the reason why it's literally a lot faster as far as conventions would go. So as far as these particular SSDs they are concerned, you can literally have the 2.5-inch. In terms of form factors, and you can also even discuss the M.2 connection there that we saw in our previous images as far as your specific setup there is concerned. So when you look at things like performance variables, read-write performance is something that you can discuss when you're looking at your SSDs. You can also even look at, so sequential read-write. Obviously, remember sequential is following a specific format. When it's randomized, on the other hand, it's accessing content in any distinctive fashion without actually following a specific a sequence or a specific a format, if you want to look at it from a different point of view. So you've got sequential read-write performance as a measure to look at how much throughput associated with these particular components. Then you've got random read-write performance. And then you can also even discuss latency, like we've mentioned before when we're looking at RAM. With the latency that is there, how long does it take for the delay in terms of accessing content? Remember, when you're looking at it from a traditional point of view, like we've been saying for a couple of moments now, because of that whole issue of the spinning, the actuators with the read-write heads, obviously access time is a lot slower because you've got mechanical parts that are there. But in an environment that you don't have mechanical parts, that particular latency is obviously a lot less visible or noticeable when you're looking at it from SSD environments. But obviously, when you're comparing SSD with SSD, you obviously need to look at things like your capacities. You also need to look at, again, like I was mentioning earlier on, what type of architecture has been used. Is it single cell or multi cell environment or technology when it comes to configurations? I think that's the reason why you find that even if it's the same capacity, some particular SSDs are slightly more expensive than the other. This is just looking at the technology that has been used in terms of configuration. And at the same time, what you're also looking at is the type of latency that is there. So if you want to look at it from a different point of view, from a cost environment, so you've got multi-level cell technology. This is normally associated with the term MLC. So this is literally less reliable than the single level environment. So if you look at it from a different perspective, you also have single level, which is literally more efficient. Cell. And this is SLC there. So this is something that you can also take into consideration as far as your specific setup is concerned. And then naturally, the third, like we've mentioned, the third type there that you can discuss is your hybrid drives. All right, and that's your typical HHD that we mentioned before. And like I said before, just combines a flash memory with the spinning platters to provide fast and literally reliable storage there as far as your setup there is concerned. All right, so like I said before, the part that is associated with your SSD is the one that is normally used for booting and running your apps. And then on the other hand, the hard disk drive part of it, excuse me, is the one that is actually used for mass storage. So you normally find, if you're looking at it from a proprietary point of view, Apple machines would use a Fusion drive that literally uses the same concept. So Apple computers use what is called a Fusion drive, which is offering literally the same concept or same architecture or same configuration associated with hybrid drives that are there. So what it does is it will separate the hard drive and SSD as far as your specific setup there is concerned. So when it comes to such content as connectivity, all right, we talked about interfaces before. All right. So an interface is that go between that enables two particular entities to literally relate with each other or communicate with each other, if you want to look at it from a different point of view. And you've got different interfaces naturally that were associated with hard drive connections. All right. As far as your specific setups they are concerned, so you had parallel comms. Remember, Parallel's main drawback is that shared communications along a communications channel, as compared to Serial, on the other hand, that looks at dedicated point-to-point communication. That's the reason why it becomes literally a lot faster. So if you want to look at the whole concept of what's happening as far as these connections they are concerned, you've got something along these lines. So these are the typical types of connections associated with your hard disk drives. All right. So you had connections associated with advent of your hard drives in the early 80s to the early 90s. Then you had IDE conventions, or what they call parallel advanced technology attachments, in the early 90s to the early 2010s. And then the M2, we're talking about a couple of seconds ago. And then serial advanced technology attachment, also known as SATA. And then you've got a serial attached SATA as well from 2005 all the way to today. So what these particularly enable for is just to remember the controllers we've mentioned in previous sessions. These controllers are the ones that are responsible for just enabling connectivity on a physical platform, and also provide for that interfacing of your machine, understanding or being able to communicate, especially obviously the central processing unit, being able to communicate with the device that has been plugged in, as far as your specific boards they are concerned, or as far as the specific configuration would go. So what was created is what is known as an advanced technology attachment standard that enabled connectivity of these particular drives or storage platforms to your particular motherboard, to enable interfacing between the CPU and the distinctive hard drive or storage component, not just on a physical platform, but obviously within the abstract environment as well. So this particular ATA was then subdivided or broken down into both parallel and a serial. And if you want to look at it from a different point of view, so if you go back, we're going to be doing a lot of going back and forth as far as our images as well as our notes here is concerned. So if you go back to what we had in terms of our notes here, we had the ATA I was talking about a couple of seconds ago. So ATA, which is short for Advanced Technology Attachment. And this particular platform is just an interfacing, an architecture that was designed to enable communication of your CPU chipset and controller, and ultimately the actual component that you've got there. And as far as this particular ATA there is concerned, you've got parallel and you will also find serial communications there. All right. Obviously, if you look at comparisons, your parallel slightly slower because you've got shared communications, and then your serial a lot faster because it's dedicated point-to-point communication there. So typical examples of what this would obviously be known as is your parallel ATA, and then you've got your serial ATA, which is also known as SATA, right? So current standards are obviously using SATA as far as your environments there is concerned. So with your uh, parallel advanced technology attachment there is normally associated with the term integrated drive electronics. All right. So normally your IDE or integrated drive electronics is something that references a hard drive that has a built-in interface or built-in controller. All right. So if you want to look at it from a different point of view, literally almost all drives have or IDE drives. But initially, IDE was associated with parallel. So normally you might find that every time that a lot of techs out there, a lot of individuals discuss the whole concept of IDE, what they're actually mentioning is they're actually discussing parallel ATA. But like I said before, literally all drives now, parallel or otherwise, obviously parallel being an obsolete standard now, would have an inbuilt controller that enables direct interfacing or communication with chipsets as well as your CPU environments. So if you want to look at what the parallel configuration would look like, I'm going to show you an image in a moment, but you'll discover that ATA started from version 1 all the way back in the 90s to version number 7, which is normally associated now with your version number 7, that literally introduces the whole concept of the SATA environments as far as your specific setups there are concerned. So if you want to look at what we've got as far as images are concerned, you can have a look at what we've got here on the screen. So we're initially discussing those connections, so that's where the PATA and the SATA environments, they come into play. So if you want to look at it from a physical point of view, naturally, this is what your basic PATA cable would look like, also known as a ribbon cable. So this is for the older computing systems as far as your environments there would go. And like I said before, this is literally an obsolete standard now. It doesn't really mean that you won't encounter older machines that have connections that are associated with parallel, but literally for you to actually find drives that are being sold in the stores and so on that would accommodate for these, it's a rarity because these particular drives are now, or these particular connections are literally just obsolete in terms of connectivity and so on because of the limitations that are associated with parallel comms, right? So the third version of this ATA environment typically introduced what is called SMART, which is short for self-monitoring analysis and reporting technology, which was typically a program that was written to check, to have the drive self-check itself, if you want to look at it from a different point of view, to see if everything is working without any distinctive issues before you can have your either OS loaded and your machine having booted to your desktop as an argument. So this SMART was all to do with just checking for any errors that were within your specific drive itself. And then it would report these errors that, okay, look, this particular drive has got bad sectors, for instance, or bad sections that are there that might need to be fixed, either within the software environment or within the physical sense. But normally, if you've got bad sectors or sections of your drive that are difficult to distinctively use, literally what you're typically looking at there is a complete replacing of the actual drive itself, just to avoid any discrepancies that might occur. So if you want to look at what the actual drive would look like, That's a drive that would accommodate for your your parallel connections rather. And as you can see, the actual power connector for these particular drives was the one that we looked at in our previous session, which is the Molex. So your Molex power connector was the one that was responsible for powering up a IDE drive, or parallel advanced technology attachment drive. And then obviously what you see on the left-hand side there in terms of the actual hard drive itself is where you'd plug in your ribbon cable associated with basic connectivity. But naturally, with advancements of techno, serial advanced technology was created, and this would then obviously enable the whole concept of faster connectivity, if you want to look at it from a different point of view, because literally parallel advanced technology attachment platform in terms of problems was that firstly, you had those ribbon cables that would typically cause problems in terms of airflow within the actual system and unit itself. So if we go back here, look at what that cable looked like. So you can imagine if you've got a couple of these cables incorporated, and probably just two of them in this particular instance, just for argument's sake, they can seriously hinder airflow within the actual system unit itself. So that was one of the major problems associated with parallel advanced technology attachment cabling or technology in general. And then the other thing is that the cable length as well was rather long. You're looking at about 18 inches. And that is obviously problematic in terms of again, the whole concept of sending and receiving signals along that particular cable. The other thing also that you can discuss is that these particular architectures were not hot swappable, which meant that if you needed to change a drive, or if you needed to remove a drive, or if you needed to literally plug in, what you were looking at is to actually, you needed to switch off the computer system, plug in or remove, and then boot the machine again. So that can be a bit of a cumbersome process when you're looking at basic functionality there. So the other thing as well is that there were limitations in terms of throughput, which is the speed. So these were all problems that were experienced with parallel advanced technology attachment. That's the reason why SATA was typically then created, to address those issues I've just mentioned a couple of seconds ago. And because serial creates a point-to-point communication, typically you find that both magnetic and solid-state drives and optical drives obviously would deal with what they call a host bus adapter that would enable for a faster communication or interfacing between the actual devices there. The cable is a lot thinner, so airflow issues were dealt with as well in that specific environment, and the length of these particular cables was a lot shorter, so 18 inches compared to 1 meter, which is about 14 inches. So again, that was a plus associated with SATA conventions there. So if you want to look at what then SATA looks like, so that's an image again of what's happening as far as your power connector when you're discussing the whole concept of parallel advanced technology attachment. That's what your SATA power and data connectors would look like. You already are familiar with SATA power from the power supply environment. What you find as the orange cable there in that particular image is the one that is associated with data. So if you compare now, literally the cables are a lot thinner, airflow issues sorted, faster communication in terms of interfacing, access to content as well in certain instances, and then also looking at the whole issue in terms of shorter cables, which would make it a lot easier as well from an airflow point of view. So if you want to look at the actual speeds associated with SATA, if you want to go back here, let's see if we can go back again to our notes. So SARTA's biggest advantage, really, with the time it was introduced, is the whole concept of speed. So if you look at SARTA here, or a Serial Advanced Technology Extended, what you're actually discussing is that you were looking at comms that were literally about 30 times or so faster associated with your environment. So three distinctive, so SARTA would literally come in three distinctive speeds. Literally, you're looking at about 1.5 gigabits per second. And then you've got 3 gigabits per second. And then you can also discuss 6 gigabits per second as far as your environment would go. And then obviously the maximum throughput. Right? So this is different variety, the varieties that are associated with your SARTA connections in terms of environments there. So obviously, if you're looking at throughput, you literally are looking at a throughput of about 100. So literally, when you're looking at it from a distinctive point of view, the throughput now associated with SARTA is again associated with what we had listed earlier on, direct. So this is about 150 megabytes per second, actually, not bits. Remember, there's the distinctive difference there. Your small b is for your bits, and your capital B is for your bytes. 300. Mbps again, same mistake. And then lastly, 600 megabytes per second. So that's the actual throughput that you're looking at as far as your specific environments they are concerned. So ultimately, with SARTA, you also have the different types, again, in terms of convention, what you're actually looking at. So this is obviously associated with what we just mentioned there. So with that, literally what we are saying as far as the actual link with your specific environments, if you want to be very specific about it, is that with the whole concept of throughput there, we are looking at the 150 Mbps that we are mentioning. With that, you're looking at 300. And then with that one, you're looking at about 600 megabytes per second. All right, that's the, oopsie, yeah, there you go. That's the actual setup that you've got as far as your conventions would go. So you also will discuss your SARTA E and your eSARTA. So there are differences there because you've got SARTA E, which is short for, the E is short for Express. And then you've got eSARTA, which is external. All right, as far as connectivity is concerned. So if you want to look at what these would look like, so external SARTA just means that it's an external port that you can use as far as connection to these particular drives they are concerned. So if you want to look at what that distinctively looks like, we've got something along these lines. So those are your basic SARTA E connections that you find as far as your actual boards they are concerned. So you can actually see the distinctive difference between parallel and serial in terms of connectivity. And then on the other hand, if you want to look at what your eSARTA would look like, you've got something along these lines. All right, so that's the external SARTA as far as basic connectivity. So it's part of the external ports as far as the actual boards they are concerned. And then on the other hand, if you go back again, these would represent your SARTA Express. Obviously, the whole concept there is to do with the actual speed of transfer as far as your specific setup there would go. So if you want to discuss the whole concept of what is happening as far as the actual cable length, I think it's something that you also want to familiarize yourself with from a different point of view. Obviously, with external enclosures or with external hard disk drives, the enclosures will obviously enable connectivity through your USB 3.0, 3.1, or Type-C ports. Or Thunderbolt ports, if you're looking at connectivity. And obviously the drives inside these particular enclosures can include SATA hard disk drives or SATA SSDs, whichever way you want to look at it. But again, from a cable length perspective, it's important for you to realize the differences between parallel advanced technology attachment, SATA or serial, and then eSATA, which is external. It's important for you to take cognizance of that fact. So if you want to look at it from a different point of view there, as far as basic cable length is concerned, something that you need to familiarize yourself with, what you actually are looking at is so as far as basic cable length there is concerned, you've got your parallel advanced technology attachment, 18 inches. Then you've got your serial, which is looking at maximum length of about 1 meter. Remember, this 1 meter is equivalent to about 40 inches, which is, no, actually my mistake there. It's actually a lot less. And then you've got your eSATA, which is about 2 meters. So it's important to familiarize yourself as far as these particular cable lengths there are concerned. Right. So another technology as well that you can also discuss when we're looking at the whole concept of what is happening as far as your computing mechanisms is concerned is what they call a non-volatile memory express environment. So it's I think it's still the same concept associated with the whole architecture with SSDs, but normally comes in with the M.2 format as far as your configurations would go. So another type that you want to familiarize yourself with is what they call NVM. I think I had mentioned NMV earlier on. It's actually NVM. And that is short for let's write this properly. So that is short for non-volatile. Non-volatile memory express. So this is the memory. All right, so this particular architecture literally supports communication connection between the OS and the actual SSD directly through your bus. So instead of actually having to go through a controller, it plugs in directly, or it enables direct to the bus communication. So that it becomes a lot faster as compared to your generic SSDs that are plugged in through a controller. So remember, your controller acts as an interface, then that then enables connectivity to your chipset, connectivity to the CPU. But when you've got direct connectivity to your distinctive bus, then it means that you've got direct comms with the CPU without actually having to go through the chipset or providing some type of generic interfacing that is there. So it's got very high speeds that you see there, and generically it uses SATA-E in terms of the actual speed conventions there. So this would typically use SATA-E or SATA Express. And again, like we mentioned before, you're looking at enables direct to bus comms, all right? Enables direct to bus. Okay. Communication. So obviously what this distinctively then means, direct to the bus or direct to bus, is that it's a lot faster because you've got direct linkage or direct communication to your actual CPU. So another type of architecture that you also want to familiarize yourself with is what they call SCSI. So you can also discuss SCSI. And this is short for small computer system interface. And as far as this particular setup there is concerned, are literally associated with your servers. All right, when it comes to storage, when it comes to basic configuration, your SCSI is the one that is normally associated with your server environment. Still, literally uses a variety of ribbon cables depending on the version. So it's a bit of an old architecture if you want to look at it from a very specific point of view, but usually reliable when it comes to these specific environments, because it provides rather a lot fast and robust storage as far as your particular servers and storage arrays they are concerned, because you can look at speeds of up to 12 gigabits per second as far as transfers they are concerned, which is obviously a lot fast. And you find that your serial advanced or serial attached SCSI. So you also can discuss what they call SAS, which is your serial. Serial attached SCSI. And this obviously, instead of using the generic parallel comms or ribbon cabling, uses your SATA conventions there. And that's the one that I was talking about, that would then provide speeds of up to 12 gigabits per second, which is rather fast as far as conventions would go. All right, so these are just some of the technologies and architectures that are there. Now, when you're looking at computing systems, all right, I think it's important to realize that literally the most important component or the most expensive component, or the most, or if you want to look at it from a different point of view, maybe I think you want to be very specific. The component or the entity or the thing that is priceless when it comes to computing or when it comes to ICT is your data. All right, every other gadget can be replaced. Every other software can be reinstalled, whichever way you look at it. But whatever is stored on a hard drive, or whatever is stored on an optical drive, whatever is stored on flash media or a thumb drive, the list will go on and on. Whatever is stored on secondary storage platforms or media is the most important and literally the most irreplaceable content or entity or component that is out there. Because like I said before, this particular content rather can be videos of your 5th birthday, just for argument's sake. If you lose that, there's nowhere else that you can get it. It's not replaceable. That's the reason why it becomes priceless. I think the whole issue of me saying expensive, I think it's not applicable really, because it's priceless. You can't put a price to it. So images of your holiday, the list will go on and on, or documentation. Again, the list will go on and on. If you lose that, then literally the whole concept of you having to use the machine becomes null and void. So it's important to find ways and means to try and safeguard this particular content that is stored, or safeguard the data that is there as far as these particular drives are concerned. So there's a concept associated with what they call fault tolerance and then disaster recovery. All right. So obviously, fault tolerance looks at trying to safeguard against a foreseeable disaster or problem or issue, and then disaster recovery is trying to salvage something when a disaster has already occurred, or when a problem has already occurred. So these are things that you need to consider when it comes to the whole concept of storage. So you've got, like I just mentioned a couple of seconds ago, fault tolerance. So fault tolerance, trying to safeguard against a foreseeable disaster. Typical examples is, I think we were talking about the whole concept of blackouts in the power supply discussion. And we mentioned the fact that to try and avoid the total loss of power, that can happen at any time. You can have a UPS incorporated there. So that's what fault tolerance is all about. You're trying to safeguard against a foreseeable disaster. In the example that I just gave, what's the foreseeable disaster? My power, I'm myself losing power in its entirety. So to ensure that I can still work on my machine, I can have a UPS or uninterruptible power supply in my environment. And then you can also discuss the whole concept of disaster recovery. So obviously here, what we're saying is that particular issue or disaster or problem has already occurred, rather. And then what you're trying to look at is trying to safeguard or trying to salvage from what has typically happened. So in your hard drive environments, or when you're talking about mass storage, again, going back to what I'd mentioned a couple of moments ago, that you try to safeguard the data that is stored there, because there's no way you can replace that data, right? I mean, if you're looking at it from the examples that I was just giving, if it comes to images, if it comes to clips, if it comes to that particular type of content, there's no way you can recreate a fifth birthday moment, right? There's no way you can recreate a holiday moment in certain instances. Obviously, you can go back, but that whole capturing of the moment is not the same as the original, if you want to look at it from a different point of view. So it's important to find ways and means to try and safeguard whatever data that we've got stored, confidential or otherwise. So a technology was created to try and protect against loss of data, right? And remember, loss of data in certain instances doesn't just always mean that your hard drive fails or your hardware fails. You can even discuss the whole concept of your components being stolen or your machine being stolen and so on. But obviously, in that environment, what you're actually looking at is storing content probably in the cloud as a measure of safeguarding. But when you're looking at it from a specific hardware environment, your a RAID is typically responsible for trying to safeguard against the loss of data in terms of accidental deletion or accidental damage of that particular data, or the actual failure of your distinctive drives. So this particular technology that was created to try and safeguard against loss of data is called RAID. Right, so RAID is short for redundant. Remember, something that is redundant is redundant array of independent some literatures might even mention inexpensive, but I think the current applicable term would be independent disks. Right. So this is an architecture that was put in to try and safeguard loss of data. Like I was just saying a couple of moments ago, remember, something that is redundant is something that is if you want to look at it in this particular aspect, is something that in a dual format, or something that if you want to argue probably repetitive, you've got the same thing of something. That's where the redundancy comes into the foray there. So this particular architecture was put in place to try and safeguard against loss of data. And you've got different types of RAIDs that are out there. So now what we're actually saying is that you've got two or more drives having exactly the same data, so that if one particular drive malfunctions, you can still distinctively access your data from the other drive. So in essence, it's just literally looking at backup in a different sense, where you've got more than one distinctive drive having exactly the same data. So in order for RAID to function appropriately, both software or hardware related, you need to have in its basic format or basic sense at least two drives. All right. So a typical example of what I'm talking about, obviously you see some of the relevant images there. If you were to look at it from a different point of view, we are saying that you've got two distinctive drives. So normally, so this is drive 1 and that's drive 2. Drive 1 will have data. Drive 2 will also have data. So that in certain instances where drive 1 malfunctions, you can still salvage your data from drive 2 and vice versa. So there's different type of RAIDs that are associated with mirrored and duplex drives, associated with the whole concept of what they call striping as well. But striping is not really a RAID, because what happens with striping is with those two drives that we're talking about, instead of writing complete data sets associated with the environment, what striping normally does is to write pieces of the data across the drives that you've got. So remember, that's drive 1 again, that's drive 2 as an example. So you've got data written across. Should, for argument's sake, drive 2 malfunction, it means that if you want to then reconfigure your data or salvage your data or try and get your data back, what you have in this particular instance is just content that is on drive 1, which is DA. You actually missing the TA there, all right? And then if you look at the previous example I was talking about, which is associated with mirrored or duplexed architectures, should drive 1 malfunction, we can still salvage the entire data set from drive 2. So that's what, in a nutshell, that's how particular RAID architectures function. There are different types of RAID that are there in accordance to the actual architecture that is being used. So if you want to look at what I was discussing earlier on, if you look at, again, let's see if we can quickly switch over. Where were we? 2 seconds, yeah. Okay, so this was the last image that we had initially incorporated there. So that was eSATA. And then I think a couple of moments ago, we were discussing the whole concept of NMV. And I was mentioning the fact that you're looking at actual direct connectivity to the bus. That's the reason why your NMV becomes a lot faster as your generic connections, because you have to actually go through a controller. That controller then needs to connect to a chipset. That chipset is then directly linked to your CPU. But if you look at the image that we've got on the screen there, what you're literally looking at is that your NMV architecture looks at plugging in directly to the bus. So it's got direct linkage to the CPU. It doesn't actually have to go through your chipset environments there. All right. So that's something that you can also take into consideration when you're discussing diagrammatically the whole concept of what is happening as far as your NMV there is concerned, right? So on the other hand, this is a typical example of what your RAID architectures would look like. So this is RAID 1, also known as mirroring, all right? So both of the drives would have the same content, Both of these drives will obviously have the same drive letter as well, because remember, you're just duplicating exactly the same content on these particular drives. So like we were mentioning a couple of moments ago, should one drive malfunction, then naturally you can still salvage your data from the other drive. This one is slightly slower. Why? Because you only have one controller that you're using. So you've got one controller that is responsible for both the drive the drive is acting as the original drive and the backup drive, if you want to look at it from a different point of view. So the read-write processes, regardless of you either running SSD or traditional environments, the read-write processes are actually happening through one particular controller. So when you're writing data to one drive, the same controller is being used to write data to the other drive as well. So that's where the slow and this comes into the foray there. And it's the same concept when you're actually reading content from it. So you only have one controller that is responsible for reading and writing for both drives. So that's where the slowness there comes into the picture. But again, you've got redundant drives, meaning that if one particular drive malfunctions, you can get your data completely in its entirety from another drive there. And then you also have what they call duplexing. So if you look at this image now, on the other hand, you've got the same architecture. The only difference now is that you've got dedicated controllers for each one of the drives that are there. So you've got a dedicated controller for one of the drives, another dedicated controller for the other drive. But this one is a lot faster. Why? Because of that read-write process being associated with an individual or with a dedicated controller for obviously each of the drives. And then naturally, both of those drives are assigned the same drive letter. So mirroring and duplexing literally are redundant. The only difference is that when you're looking at a mirrored drive or a mirrored architecture, it's a slightly slower because you're using one controller for access. With this one, it's slightly faster. Why? Because you've got dedicated controllers for each of the drives that you've got there. And then what I was mentioning earlier on about the striping part is that this one is normally associated with what they call RAID 0. And if you want to be very specific about this, if you want to be very pedantic, it's not actually a RAID because you're writing data across, right? And like I said before, should one of the drives then malfunction, naturally what that typically would mean is that you can't salvage the entirety of your data from the other drive. So it's fast, but it's not safe because you've got pieces of data that are written across the drives there. And then naturally both of the drives are assigned a drive letter as far as your specific setup is concerned. All right. So just argue, if you want to look at it from a different point of view, imagine yourself saving a Word document for argument's sake, and then part of that Word document is saved on one drive, the other part of the same document is saved on the other drive. So if one drive malfunctions, you only have a piece of that file. Maybe look at it from a different point of view. So that's what the RAID architecture is all about. But obviously, as technology advanced, you've got different types of RAID that then try and allow for checking of the correctness or the integrity of your data. And when we're discussing RAM, we discussed the whole concept of parity. And you also have RAID that deals with what they call extra bit parity and distributed parity. So RAID 0, again, not actually a RAID. RAID 1 associated with both mirroring and duplexing. And then you've got RAID 5, which is associated with distributed parity. And with this one now, you are now using an extra hard drive or extra set of drives that are just used for checking. Remember, parity is a way of checking for errors. So you've got a set of drives or a set of the drive that is there that is used for checking. Then you've got RAID 6, which is associated with striping with extra bit parity. Again, you've got an extra set of drives there that are used. So at least 4 drives. It means that you can literally afford to lose 2 drives at any given time. And then you've got RAID 10, normally incorrectly known as RAID 10. It's actually a nested drive or a nested environment that uses both RAID 1 and RAID 0. RAID 1 obviously taking precedence there. And then you also have RAID 01 or 0 plus 1 rather. RAID 0 taking precedence there. So if you want to look at it, if you want to go back, let's see if we can go back here to our slides so to see if we can elaborate this a little bit more. So what we are mentioning is, if you look at it from this point of view, maybe let me add 2 more slides there. Hopefully these will be enough. So when you're looking at your RAID environments, like I was mentioning earlier on, you can discuss, okay, let's see if we can change. We can discuss, maybe let me put this differently. All right, so you got RAID 0. And this one is normally associated with what they call disk striping or striping. So not really a RAID here, but it's incorporated there just as an architecture that can be combined with another. So this one you'd need at least 2 drives. Obviously, if one drive fails, then you lose. You can argue that you lose half of your data, if not more. And then you've got RAID 1. And this can either be mirrored. So this is mirroring, come on. So mirroring or duplexing, one and the same. The only difference now is that one uses 1 controller, the other one uses 2 controllers. And with this one, you obviously need at least 2 drives, or you can afford to have 1 drive malfunction. So that's normally what they call the number of functional failures in any given environment. And then you can also discuss RAID 5 that I was mentioning earlier on. And RAID 5 now deals with distributed parity. So this is distributed parity as far as this particular setup is concerned. So with this one, you need at least 3 drives because you've got 2 of the drives that are used to store the data, original and backup, and then the extra drive, the third one, is the one that is used for checking for these particular errors. And then you can also discuss, I think that was the third one we're looking at, you can also discuss RAID 6. And instead of using distributed parity, this one uses extra bit parity. So we can just say extra parity or extra bit parity. And then you can now talk about the nested RAIDs. So your nested RAIDs can either be RAID 1, 0. So this is nested. So this just means that it's a combination of both RAID 1 and RAID 0. The only difference here is that what literally takes precedence there is your striped environments. You can also even discuss again another type of nested RAID, which is 6. That is RAID 0 plus 1. Again, another nested RAID. Another nested RAID there. So obviously this is dealing with mirrored stripes. So the other one is striped mirrors, and the other one is dealing with mirrored stripes. As far as your setup is concerned, just a combination of both RAID 0 and 1, and the other one combination of both RAID 1 and RAID 0 there. All right. So obviously with RAID. So again, with RAID 0, at least 2 drives, RAID 1, same difference applies, RAID 5, at least 3 drives. Why? Because you've got your extra drive that is being used there as a network checking platform. RAID 6, you'd need at least 4 drives. But obviously it's slightly more pricey because you now need more drives there as far as your array is concerned. But you can afford to at least lose 2 drives there at the same time, which works as far as your setup there is concerned. So if you want to look at the functional failures rather that I was discussing earlier on, functional failures would be how many drives you can afford to lose in that environment. So if you go back to our, let's see if we can have our images put back. So this is what we're talking about. So when you're looking at functional failures, what we actually mean by this is that with RAID 0, like I was mentioning, the minimum drives you need is 2. You cannot afford to lose anything here. That's the reason why I was saying it's not actually a RAID, because should you lose any drive, then it means you lose a massive chunk of your data. And then on RAID 1, you've got minimum of 2 drives. Number of functional failures 1, which means you can afford to lose 1 drive in that environment and still be able to access your content from another one. RAID 5, minimum number of drives is 3. The extra one is used for checking distributed parity, checking for correctness or integrity of your data. So you can also have one functional failure there. You can only afford to lose 1 drive in that scenario, because if you lose anything more than that, you lose the entirety of your data. RAID 6, on the other hand, extra parity, so you need another drive there used for your mechanisms. But ultimately, you can afford to lose 2 drives. You can still be able to salvage your data from 1. And then RAID 10 or RAID 10, which is interesting because just a couple of moments ago I was saying that it's normally incorrectly known as RAID 10. It's actually a combination of RAID 1 and 0 there. Those nested environments we were talking about earlier on, you've got a minimum of 4 drives and then up to 2 functional failures that you've got. So if you want to look at it from a different point of view, if you want to look at it from a different point of view, you can also have RAID enclosures where you've got an enclosure that accommodates for multiple drives to be incorporated. Remember, your RAID, like I mentioned before, can exist both software and hardware related. Obviously, the best is the combination of both, where you actually have your board, your motherboard, having an actual RAID controller that is there to accommodate for that fault-tolerant environment we're discussing. Excuse me, a couple of moments ago. So this is a typical example of what a SATA RAID controller would distinctively then look like. Something that you obviously need to plug into your PCI slots there, and then be able to utilize RAID architectures on a hardware level, the combination obviously of your software environments there. And then when you're looking at an enclosure that can accommodate for RAID, which with the multiple drives we were talking about earlier on, you've got something along these lines. So that's your typical example of a Western Digital RAID enclosure, which has your multiple drives incorporated there as far as your specific environments there are concerned. And then when you're looking at the whole concept of the solid state drives we were mentioning earlier on, your M2 and your mSATA, literally one and the same in terms of the way in which you plug them onto the board and so on. That's a typical example of an mSATA platform that you can plug in to a distinctive board. It obviously has to have a specific connection that is there to avail for connectivity as far as your environments are concerned. All right, so I think that gives you an idea of what is happening as far as your mass storage technologies they are concerned. I think we should be good to go as far as this particular session here would go there. All right, so any questions, contributions, and or concerns as far as this year is concerned? Okay, let me just have a quick look here. Okay, so Natalie, I think, okay, so this is a recorded session, so I'm sure anyone who was failing to connect should still be able to access the clip on the YouTube channel. And then Naidu there, you're mentioning that, okay, so the assignment, yes, because the assignment is June, and I think sometime in June, but like I said before, I've already uploaded a clip because you've got your colleagues that are also doing phase out, running the same assessment platforms. So there's a clip that is already there on YouTube that discusses this assignment. So I think I mentioned this yesterday, if not, yeah, I mentioned this yesterday, and I said that go and have a quick look at that clip. Should you not understand anything when it comes to that particular assignment, let me know. Obviously, it's early days, really, but it's important just for you to get an idea of what it is that you need to take into consideration when you are attempting that assessment, and obviously when you need to then submit it. And I think the only drawback currently when it comes to that assessment is that we obviously need to have a dedicated physical session that will enable you to actually dismantle your PC, take the components that you need, take them apart, take distinctive images that you'd use for the assessment, and then put the machine back together again. If I'm not mistaken, like I said before, that should be question 3 as far as your that should be question 3 as far as your specific assignment day is concerned. We'll take it from there. So have a quick look at that clip there. It's labeled as core F120 / core 5111 assignment discussion. So have a look at that one there, Tevesan, and then let me know should you not understand any content that is there. All right. Do we have any questions or contributions? Okay, so can you email? Can you please email me the link? Okay, I can do that. Can you? I can actually put it in here on chat. If you can, I will do that. But I can quickly also give you this on chat here now. Quickly, give me 2 seconds. So there, I need to copy this. All right, so link to the video, not the channel. Okay, no link to the video. So I think you already know that that's I plugged in the link to the channel there. A link to the actual video is this one here. So I'm just gonna copy that and plug it here. All right, so let me know if you've seen this in chat there, Naidu. If not, then I'll just pop your mail again. So the second link that I've just sent you, that's the link to the actual link to the assignment discussion video. So let me know if you see. Can you view chat there, Nigel? If not, then I'll just quickly send them after the session, after uploading this particular clip. Right, so do we have any other questions, contributions, or concerns? Feel free to type out on chat there if you need to speak. Let me see if I can quickly unmute you here. Give me 2 seconds. All right. Feel free to type out on chat so long. Do you have any pressing issues? Next that. Right, anyone with questions, contributions, as far as today's session here is concerned? Questions, contributions, concerns? If you're unable to type, all right, so I've just unmuted if there's anyone who actually needs to make use of their mic. Feel free to state your case. Questions, contributions, or concerns from the floor, guys? Okay, so it seems everyone is groovy. If you do obviously end up by identifying any issues that you've got or any concerns or questions, you can always just pop me a mail. So thanks again for attending. Let's call it a day. We'll convene again for implementation of mass storage technologies or implementing your hard drives in tomorrow's session. All right. Stay safe. Keep smiling. We'll see you in the next one. Cheers.